Recording in progress.
Okay, so here are the answers I got for these problems, and I could make mistakes, so please let me know. Just gonna kind of just write it, and then we'll just talk about it. Remember, D&E means does not exist.
Yes, yeah.
Okay, so just having a quick discussion here.
F of 0, I don't think exists, but I don't see it being defined here, right? It's not part of the domain. Or say it says part of the domain, whatever, just something that just doesn't exist, right? Or undefined, that's fine too. If you say D&E, I'll take that, that's fine. B of course is 0, right? C of course is 3, so you have a little dot putting up there. D technically does not exist if you don't know what it is. But if you say negative A, that's cool too. I'll accept that. See that definitely does not exist because left and right side are in different places, right? Like left is going down forever, the right side moves 2. So there's no agreement between those two sides. F at definitely is a 2. So going from the right side to the input, so the left side of course is going to be 1. They didn't ask that. G of course does not exist. The left and right side is going to reconcile with each other, right? Different. Then H of course is going to start to the left.
So hope that makes sense. We're cool with that. All right. Moving right along. That's what I got for these bad boys here. Let me clear the screen. Do all this at once. There's no graph associated with 12 or 13, so I have to look at the equations or the piecewise functions that are there, right? Okie dokie.
For 12, we can say it does not exist because, yeah, one's not part of the domain. So there you go. You have an equal sign. It's for either expression. For B, that's definitely going to be 0 because you put it into the top one, sign 0, and 0. For C, of course, it does not exist because they're both in different places, right? And they're pushed one to the left or to the right. That's going to be 1, of course. It's 0, not the same, so we can't say anything about that. This is kind of a funny one. Apparently, there's a gap between 2 and -1. It's a very odd piecewise function. We usually don't have those kind of gaps, but apparently some does. So there's no definition between -2 and -1 inclusive. So of course, -3 has to be about it. I'm fine. B of course is 4. You have to plug into the last one, which gets you 4, 6, 9, 5, 6, 4. For C, you're going to plug into the middle one. I think that was 10. That's 7.5 over. Hold on. Did I do it correct? Yeah. Okay. Yeah, let's change in my head. 7.5. And the bottom is being 9/4 minus 3/2, which is 0.7. Yes, 7.5, 0.75 is 10, right? D does not exist because the left and right side of both equations of the values. And then, of course, for E, yeah, because for left side, that's going to be 8 over 2 is 4. It's not. Wait. Oh, -2. Sorry. -2. Yeah, you don't have, sorry, you don't have the right side to it. So, wait one sec. Hold on. Let's go back to D again. You want to see anything different than DNA? I guess it could be. It could be just the left side. Use your purple one side limit. Let me think about that one because there's no right side. They don't want to give the answer for the left side limit for D. Sometimes if it's not defined, you might, well, I'll come back to that one. That one I have to ask one of the teachers for here. For E, that's 5/2. I put -1 from the right side. Yeah, just plug it in. You get 5 over 2. For F, plug in 2. Left, right side, they both equal the same thing. So they actually agree with each other. So that's good. The L to RHL. And for G, well, point is very something that does not exist. Can't talk about 0.
So would it be wrong to say it does not exist?
That's fine. Yeah, I'm okay if you say DNA. That's fine. Yeah, I mean, I just haven't defined because it's not defined, but yes, that's true too. There's nothing. We're not going to get into all the semantics of the words. That's totally fine. Okay, did work out 14 and 15. Geez, I wish I really took a picture of this because I don't want to write this out. Well, first off, in part B, I'll just kind of do it here. For part B, I got the LHL is -2. And the RHL I got +2. Obviously, the limit does not exist. The piecewise function itself is going to be x squared minus 1 over x minus 1, or x squared minus 1 over 1 minus x. This would be true if x is greater than 1. This would be true if x is less than 1. You can simplify it. If you simplify it further, you should get x plus 1 or negative x minus 1. Because when you factor this, it's x minus 1 times x plus 1. This is the weird one. When you have 1 minus x and x minus 1, those cancel, but you have to leave behind a -1. Because 1 minus x is the reverse of x minus 1, right? Just negative on the outside times x minus 1. So those go away and you leave behind a negative, which is why it's negative x minus 1. So that's really your piecewise function. And that's what we're evaluating the limits of, right? So that's how 14 works. So you have to just make sure you're comfortable doing that. For 15, I got positive infinity for both left and right hand limits. So you can say positive infinity for that or D&E, because it's not really a number. So if you said D&E, it's fine. But you said positive infinity, that's also true. The piecewise function would look like this: 1 over x minus 4 and 1 over 4 minus x. X is greater than 4. X is less than 4. So there we go. Okay, 16. What are we gonna do about 16?
Yeah, actually,
Yeah, go ahead, far away. Go. Yeah, go ahead.
What is the LHL for 15 be negative infinity? It's 1 by 4 plus x, so then anything below.
Oh shoot, you're right. Sorry. Yes, I have wrong in my notes here. Yes, if you're approaching it from the left, wait, approaching from the left side.
So then,
No, you mean the wait, from the left side or right side?
or when x is less than 4. So
When x is less than, oh, but we're using a different function though, right?
We're using this function, we're using this function. When x is less than 4, like 3.999999999, that's one of a positive number, right? Right.
oh, when it's less than 4.
Yeah, exactly, right.
No, I do have it correct. It is positive thing for both. You probably plug into the wrong function or plug in a different number. That's probably what happened. Because we're doing two different functions for each. Now, if it's 1 over x minus 4 and you're just looking at that, yes, there's going to be 2 different sides. Or 1 over 4 minus x, same thing.
Since they're both going to
Yeah. Yeah, well, they're both going towards positive infinity. Exactly right. Right. Okay. For this one, we're going to say, let me do the piecewise function here. It's going to be x squared. Now, if x is approaching 3 from the left, I have to reverse this. Actually, let's do the piecewise function first, straight up. Let's just do it like the way we're supposed to. So that's going to be just x squared. But for the other guy, you reverse it, right? And that's just going to be negative x squared. This would be true when x is bigger than 3. This would be true when x is less than 3. And let me fix that exponent. That's terrible. Let me fix that. Sorry about that. Okay. But we're only approaching it from the left side, apparently, in this case. So if you're approaching 3 from the left side, there'll be -9. So the left-hand limit would be -9. If you want to calculate the right-hand limit, it's +9. And of course, that's D&E. I think that's a typo. I don't think they meant to put the negative there. Oh, never mind. It's not a typo. It said could be only left-hand only. Okay, never mind. Okay, there we go. So it's -9 then for left-hand limit. Yeah. Yeah, totally. Yep. Exactly. And then lastly, 17. I have to work sex. I don't have it here in my notes. Remember we talked about it. You want to write it as the square root of x minus 9 squared, which is actually the same thing as x minus absolute value of x minus 9. Now it's write as a piecewise function. If I write as a piecewise function, it's x minus parentheses x minus 9. Should x be bigger than 9? Or it's x minus 9 minus x. Ah, geez. If x is less than 9. If I continue working out more, it'll be positive 9 or 2x minus 9. And Yeah, so now let's look at the other parts. If you're approaching infinity, it's 9. Approaching negative infinity, you're going the other direction, it should be negative infinity. And of course, that does not exist. Because graphically speaking, it's going to look like this, right? It's going to be here at 9, there's a hole here, and it goes that way. And then they actually do meet up. Oh, wait one sec. Oh, I'm losing my mind. Sorry, guys. It's obviously 9. Yeah. Sorry. Yeah. Sorry. It's 9. Yeah. Sorry. I was totally wrong about that. Because the LHO and RHO both meet at the same place. It's gonna be kind of like this. That's the piecewise functional look. So they do meet up at 9. That's right. It's not continuous there because we didn't define it for 9, unless you want to add that and say, oh, it equals 9 and x equals 9. If you want to do that, whatever. But yeah. Okay. Or I guess if you want to do that, apparently, but regardless, they meet at the same place. The limit does exist. All right, so that covers the homework. Let's go through the notes now. Let's see how far we get today. So lucky for you, you'll have this done. They have to watch a video with all the other guys. Oh, another thing I just thought about that popped in my head because we had a math part meeting this morning. I noticed the last test didn't go so well for some of you guys. What I've decided to do, because I'm the only teacher of pre-cal BC honor, so I can kind of do what I want. I'll make the final exam weighted more if it'll help your grade in the long run. So I'll actually calculate your grade 2 different ways. I'll drop your lowest test score and make the final exam probably worth, well, whatever percentage that test score counted towards the overall grade, I'll replace that with the final exam score. Put it that way. So if it helps you, if it doesn't help you, then we'll just stick with what we have normally. So just, the final exam will have more bearing on your overall grade, if that will help you. So I'll calculate 2 different ways for your grade. So just, or I might do maybe a mix. Maybe I'll do 3 different formulas. Kevin Morris does that, which I think is kind of clever. So maybe I'll do maybe the exam's worth 30%, but that lowest test is worth maybe a little bit. So we'll calculate different ways to see what helps you guys the most. So that's what we'll do, just, I imagine these future tests could be much easier than the last. The last test was pretty brutal. I don't imagine this stuff being challenging. Just new, but it's not challenging. Anyway, all right, just want to share that with you guys. All right, you're welcome. Yeah. Okay, finite limits. So we're going to talk about limits with x approaching infinity, or when the limit itself is approaching infinity. And just so you know, this is all about this whole thing. This whole section is all about asymptotes. So you learn about asymptotes in algebra 2 trig honors, right? Maybe even before that, I don't know. And we kind of talked about in this class, but now you actually get a deeper understanding of it from a calculus perspective, because that's really where it comes from. We introduced it well before people take calculus, so I think that's why people kind of mess it up. I think you guys are fine because you guys are honor students, but my regular algebra 2 students, they think, oh, horizontal algebra, you can't cross it because they never crossed. Well, that's a certain type of function, but they can't, like exponential, they don't cross, or simple rational function don't cross, but more complex rational functions, you can cross horizontal asymptote. You can also cross a slant asymptote or oblique asymptote. Vertical asymptotes we never cross, but maybe you can if you do as a piecewise function. You could have a dot at a piecewise at a vertical asymptote, but we need to understand at its core, what does it mean to be a vertical asymptote? What does it mean to be a horizontal asymptote? From a limit perspective, it'll make more sense. So let's talk about limits as x approaches positive negative infinity. Just so you know, this is all going to deal with end behavior. I don't want to say horizontal asymptotes because sometimes it could be slant or oblique. Oblique meaning the left and right ends maybe look parabolic or cubic. That could happen. It doesn't have to be a line. It doesn't have to be a slant. Like the end behaviors could be a lot of different things. Typically, the horizontal lines, just so you know. So that's what we're going to really look at. When x approaching positive infinity, we're looking at the end behavior, the far left and the far right. What the heck is going on with the graph? So let's start with something pretty simple. Example 1. That's just y equals 3, right? So not that bad. So y equals 3, boom, there you go. So what's the limit as x approaches negative infinity? 3. What's the limit as x approaches positive infinity? 3. So what's the limit as x approaches positive infinity if you just have a constant? Just the constant itself. What's the horizontal asymptote? Y equals k. Just that simple. That's it. So just look at it, just think about it. Yeah, if you take the limit of a constant, it's a constant. That's all. So that's the takeaway here. The limit of a constant as x approaches positive or negative infinity is just the constant itself. Just, that's all. So we're good. All right. I don't need to beat around the bush on that one. Example 2. What if you have 1 over x? Yeah, we know graphically. I'm just going to do a quick sketch. Yeah, it just levels off towards 0. Right, exactly. So in this case, it's y equals 0. So as long as you have 1 over x raised to some power where n is a constant greater than 0, like even if n's 0.1, fine, who cares? Or even root x, who cares? Because ultimately that's an increasing function for the bottom, right? Even if you have like root x on the bottom, I mean, the function itself is decreasing, but root x itself is increasing. So the bottom's getting bigger, then the top is stuck at 1. It's just gonna be going towards 0 every single time. Again, think about it. Analytically, think about it. The denominator gets bigger. While the numerator is stuck at 1. That's it. That's all that's happening. Even if you had another number like 2 or 3 or 4 or 5 or even a million, it doesn't matter. Even if you put a billion or trillion, it doesn't matter because ultimately the bottom's going to surpass the top. And that's what we're talking about, infinity. Okay. So the definition of a horizontal asymptote is essentially the line y equals b if the limit of x approaching infinity equals that constant. So if your limit equals a constant, that will be a horizontal asymptote. That's what's happening. So let's look at this one here. Actually, let me pull up Desmos is probably better, I think. Let's see here. Y equals sine x. Sheesh, hold on. Struggling here, divided by x. Yeah, if I zoom out, what do you notice is happening to the graph? Okay, that's not really good. If I just do this, it's essentially coinciding with the x-axis. Not coinciding, but getting close to the x-axis. But remember, see, but look what it's doing. It's going above and below, above and below, above and below. Because it's wavy, right? That's how sine's supposed to behave. But ultimately, those waves are getting less in amplitude, less and less and less, almost to a point where you could barely even tell a difference between that and the x-axis. Yes, there is a difference, but super, super tiny. So in this case, what's happening here? I mean, I could punch it in. Let's just do it. I don't feel like it, but that's all right. 9x divided by x. And I'm just going to value on the calculator. Yeah, it's like 0.00984. 0.00985, I'll round up. If I plug in 1,000, it's negative 0.00985. And I kind of imagine the same thing, negative 0.0000985. And if I do 100, that's interesting. There's a symmetry here, which actually makes sense because it's an even function. That actually would make sense because sine negative x is negative sine x and negative x is negative x. The negatives cancel, so it is an odd function. And actually, let me do 10,000 just to be sure that I got that positive or negative. That's negative, yeah. So that's also the same thing. 985. So the graph kind of looks like this. Like that. So in each case, it's going to be 0. So actually, there is an asymptote, believe it or not. There is an asymptote. It crosses it many times, and that's okay. There's nothing wrong with that. There's nothing wrong with that. The whole point of the horizontal asymptote is what does the end of the graph look like? How does it behave? Not this region, not like a forbidden region can't cross. Of course I can cross it. Big deal, right? So if I do like green for my horizontal asymptote, yeah, awesome, good. So you want to get rid of that misconception. I don't think you guys have that, but usually my regular algebra 2 students do. And I think it's not the teacher's fault, or it's just the way sometimes the curriculum is designed that kind of causes that confusion. But anyway, Ryan, you have a question? Go ahead.
So I guess bottom line, it's just not about what's going on for the center. It's like.
We don't care. Just bar left, bar right. That's all we care about. Yep. That's why we do it through a limit perspective now. That's why it deepens your understanding, because now you know, oh yeah, what is the limit of that function? What is it going towards? It's getting closer and closer to 0, right? When that happens. So the conclusion here is that if you're going towards infinity or negative infinity, it's just gonna be 0 in each case. And who cares if it's 2x over 2x, whatever, it's just gonna be that. So something you can always use if you have like that involved in a limit, you can kind of pull that out and just say, oh yeah, just going towards 0, it's fully fine. Yeah, if I go back to if I do this like 2x over 2x, yeah, who cares? Same thing. So yeah.
Just like it's 2x.
Yeah, I just did that right now.
But the denominator is just like that.
Yeah, it's still the same thing. Because what's happening is that they're both increasing in the same well, actually, sorry, the bottom is getting bigger than the top ever would. Because think about it, what's the range for sine? From -1 to 1, right? Unless you do an amplitude change, which we're not, right? But what's the bottom doing? It's getting really big. The bottom is exceeding the top like crazy. That's what's getting towards 0. Where you will see a difference is that x equals 0. Like in this case, I know it's gonna be 2, right? Or if I do 3, I get that. Or if I do 4, I get that. Back to x, I get that. Or if I do 2, we'll change that to a 2. And of course, you see that happening as well, right? So that's also another thing to kind of keep in mind. Now that looks like that's getting close to half. So yeah, a lot of different things happening there. Okay. Let's look at this guy. 2x root x squared plus 1. Before we even do this, I want to take a stab of what they think this will be. What do you think? Just kind of just looking at it, kind of just doing an approximation. Like, think about the bottom. What do you think that's going to be roughly like when x is approaching infinity? Yeah, exactly. And you have 2x over x, which is pretty much 2. Yeah, I expect the answer to be 2 here for each of these. Actually, I think it'll be a little different. I'm going to take it back. It's going to be this, actually. You're going to have 2 different horizontal asymptotes. I'll explain why in a sec. What you need to do is, well, you don't need to, but you should. Think of it like a piecewise function. Yeah, because ultimately it's kind of like this. Because root x squared plus 1 is approximately root x squared for large x. And what's that? That's the absolute value of x. We know this. So when x is negative, overall it's -2. When x is positive, it's going to be +2. So we analytically determine it. I've kind of done it right here for you guys. Already done it for you guys. It would just be 2. If I were to punch this into my calculator, let me do it right now. So let's see here. Parentheses 2x root x squared plus 1. Yeah, I get negative 1.999999, right? More of the same jazz here. Actually, there's a few other things happening. But that's just like crazy. A bunch of nines. And then here it's a positive 1.999. And 1.999999 dot 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 dot. Yeah. So yeah, that's what's happening. Does that make sense? And graphically speaking, if I were to graph that in the standard window, yeah, graph kind of looks like this. Kind of like a logistic function in a way. So have we talked about logistic functions? Oh, that's a missed opportunity. I should have done that. All right. Well, no time. Maybe I'll squeeze it in at the end. All right. So remember all the limit definitions. They still apply even if x approaching positive or negative thing. We saw that when x approaching a or b, but they still apply. All these different properties. So there's, so we can use that for down below. So let's do it now. Yes, can I help?
I need to record sounds for my H spot.
Sure, that's fine. Go ahead. No problem. Make loud sounds now. All right. Example 5. Let's do sine squared x. So if I do sine squared x, let me punch in my calculator. Sine x, no problem. Shoot. Well, I gotta switch my mode to radians, Z trig. Okay, here we go. So I kind of don't know what's happening because it isn't kind of going back and forth between 1 and 0, so there is none. Yeah, I want to say oscillating so much. I mean, I guess it could, but we just don't know. I have no idea because it goes back and forth between 0 and 1. So you just don't know. Yeah, totally. Okay, let's keep moving. All right, so analytically, example 6 involve find limits x approaches positive or negative infinity for rational functions. So we should know this by now, right? Like, generally speaking, focus on the highest degree, where n's the highest power in the denominator, m's the highest power of the numerator, I think. Or actually, sorry, we'll divide each term by the highest power of the denominator. So, yeah, go ahead.
How would we be able to find that?
You can't. We do this. We do it graphically. Yeah. Sometimes you just can't. Yeah. Yeah. Analytically means like doing some algebra skills. That's what it means. Which actually, I don't know if I quite did that. Well, I kind of did for example 4 because I switched it to absolute value, but I still looked at it from a numerical perspective too. Yeah. 1 over x. Actually, I think 1 over x I did numerically. The more I think about it now, but we know what's going on there. So, all right. So here's what you want to do for these problems. For example 6. You're going to multiply top and bottom by 1 over x cubed. So it's going to be 2 over 3 minus 2 over x squared. Okay. What happens when x gets really large? What happens? Just goes away, right?
Would we divide everything by x plus 4?
No, x third. Why x4? What's our highest exponent of the denominator? Because that's what we're being tasked to do, right? The highest power in the denominator. For example 6. Which one? Are you looking at the wrong example? Yes. Yeah, you can, but that's the more of a numerical perspective. That's what you guys were taught in algebra 2 trig honors. No, totally. You could look at, yes, you should compare the degrees of top and bottom. And sometimes I like to call it bottom heavy. If the denominator is a higher power than the top, yeah, then it's going towards 0. If they're the same, it's the ratio to leading coefficients. If the top is higher than the bottom, called top heavy, then it's just yes, use the next division to get the end behavior asymptote or the oblique or slant, but the limit itself is positive negative infinity because it's going up or down forever. So in this case, that just goes away, right? That just goes away. So it's just 2/3 in each case. Because 2 over x squared approaches 0 as x approaches positive or negative infinity. So that little part, that complex fraction vanishes when x is going towards positive or negative infinity. You're stuck with 2/3. That's how you do it analytically. You got to find the highest degree at the bottom and multiply both top and bottom of the fraction by that reciprocal. Very good.
Just thought that for A was minus 2.
No, it's negative. It's both 2/3. Both 2/3, right? So let's do it again here. I mean, I know the answer is going to be does not exist or positive or negative infinity. So there are no. Oh yeah, sorry. The horizontal asymptote here, sorry, is y equals 2/3. Yeah, I forgot to say that for example 6. So for example 7, what I'm going to do here is I'm going to multiply top and bottom by 1 over x. So you always do it to the highest power of the bottom. So it's 2x cubed minus 7x over 3 plus 5 over x. So that goes away, but what are you stuck with? Yeah, totally. Yeah, if you're going further to the left, that's negative infinity, by the way. Going further to the right, that's positive infinity. There's no horizontal asymptote here. Yeah. Now, so you guys, I think you're saying about long division or synthetic division. That will come back in AP Calculus BC or AB, whichever AP Calculus class you do, because we'll need to do that for some other calculus techniques down the road. Because we do need to kind of like know how to re-express that rational function differently. We're not going to do that for this class because that doesn't really play a role, but that will come back eventually. But yes, if you want to find the slant asymptote here or oblique, you have to do long division or synthetic as possible. Okay, go ahead.
Oh, I was gonna ask, I got three more fun tables from next year on the bottom. So the 2x cubed minus 7x over 3 would not be like a slant or the other type of that and behavior?
Actually, no,
Or would
actually, it would be. I think. Well, I don't feel like doing the division right now. I think that might be the slant asymptote. I think it is.
you know that there's no horizontal asymptote, it's because it's simplified.
Yeah, it doesn't simplify the number exactly. Exactly a constant, right? Here. I know the answer is 0. And that's just because the bottom has a higher exponent than the top or higher degree. But again, you multiply top and bottom by 1 over x, 4. So it's 3 over x. That's 0 plus 0 over 5 minus 0. You get 0. Okay. Here, I would just look at it graphically. This is numerically, but yeah, just look at it graphically. This is why I spent all these years doing this stuff, so you guys can just do this quickly. And by the way, why are we spending so much time on limits? Actually, I haven't really had that discussion with you guys. We will talk about the derivative, which is the rate of change, and this is differential calculus we're doing. We'll do more differential calculus in the fall. Differential calculus, like the first semester of positive calculus. Differential calculus is about the rate of change. About like maybe if you're looking at position function in physics and you want to see how fast you're moving, or your acceleration, if you have a velocity function, you're looking at the rate of change of position versus time to get velocity. You're looking at the rate of change of velocity versus time to get the acceleration. Those are derivatives. But also you could use it with like with how fast people are getting COVID infection rates, right? Like you see it like when you see the flattening of the curve, that's actually all calculus, right? Because you look at how steep the curve is at certain points. Sometimes when the curve is very steep, there's high infection rates, right? Or even like if you're looking at a stock price, like if a stock's moving up really quick, a lot of times people who invest or deal with financial stuff, they gotta look how fast it's gonna move. Maybe it's gonna start slowing down. If it's not, if it's really slow, maybe it's gonna start, speeding up, and you're gonna start making more money. We have to understand how limits work in order to understand derivatives. We're gonna do derivatives eventually after spring break, and so that's where I spent all this time, just so you know. But in order to do the limits, we also have to understand how these graphs look, and that's why I spent all these years teaching you guys, hey, ETX looks like this, 1/2 TX looks like this. So in each case, I don't feel like writing this over and over again, but I guess we will. The limit as x approaches negative infinity of e to the x, and the limit as x approaches positive infinity of e to the x. Well, that's going to be 0, and that's going to be positive infinity. Here, that's going to be positive infinity. That's going to be 0. Just look at the graph, right? And for C, same as B. I don't feel like writing again. So, because they're both decay functions, right? Because remember, e to negative x, e is like roughly 2.7, but because of negative exponent, you flip the base, right? Because 1 over 2.7, that's decay, right? Because that base is between 0 and 1 for part B. So not that hard. I mean, if you want to plug in numbers, go for it. Plug in like 1,000 for x and negative 1,000 for x. Graphical might be better too. So, okay, we're good? Okay, rolling right along. Okay, now here, it looks really wacky, but don't let it freak you out. Actually, you could do is this. 7 minus 0, 0 plus 3. Right? Because we already know.
That's constant. That's constant. No, that's 0. No, that's 0. That's decay. That's approaching infinity. That's it. That's all we did.
It's using the limit properties. When do we get out, by the way? No, no.
35.
Okay, we got some time. My goal to really feel comfortable is get the part C squeeze theorem. Actually, I need to brush it on my side. I do know how it works, but I just don't want to botch it. And I think just we'll wait till we come back from break. But in order to kind of feel a sense of completion with limits, it'd be good to do all the infinite limits. So let's do page 5, about half of page 6, and then we're done. So just 3 more examples. Okay. Analytically determine the limit x approaches negative infinity of that. Now remember, this is a piecewise function. We know this. X plus parentheses, or actually be x minus x plus 5, or x plus 5. As x is less than negative 5 here, or x is greater than 5. So if I write again, clean it up, negative 5 or 2x plus 5. Does that make sense? So that's a negative 5 there, my bad. That's a greater than symbol. So there we go. Negative 5 is, goodness. Let me do the graph over here because I kind of messed up. Negative 5 is right here. And here's negative 5 again. And it kind of looks like this. So clearly that's just negative 5. Sorry. Yeah, negative 5, yeah. There you go. So pretty simple. Just rewrite it as a piecewise function. That's how you show how you show your analytical work for that problem. Questions? No? We're okay. Okay, next part are going to be infinite discontinuities. I'll just abbreviate it, or a vertical asymptote. Because now x is approaching a number but the limit itself is going towards infinity. Like 1 over x again looks like this. I'm gonna be a little more precise with this one. So that's going to be negative infinity. That's going to be positive infinity. So the equation of the vertical asymptote is x equals 0, but this does not exist, of course, right? So that's what's happening. As the limit approaches infinity, sorry, if that's approaching some number, but the limit itself is going towards negative infinity, that gives rise to a vertical asymptote. Okay, that's how we get vertical asymptotes in the first place. So just to kind of think about it, if the limit of the function positive or negative infinity as x approaches a finite value, then we get a vertical asymptote. That is at its core what a vertical asymptote is. Like a lot of students just think, oh, it's just what makes the bottom zero of the rational function. True, but it could be a whole. That could happen, right? You could have like 2 factors that are identical in a rational expression, and they cancel out. In that case, that would be a whole. That would be a point discontinuity. But for an infinite discontinuity, yes, after you simplify, what makes bottom zero true? But at its core, that's what this is. As x approaches some number, finite value, if y is going towards positive negative infinity, that gives rise to a vertical asymptote. That's where it comes from. That's the whole point of it. So when this happens, x approaching a from the left or a from the right, if it's, it could be either one, positive negative infinity for the outcome. That's what happens. That's the true definition. That's the true definition of vertical asymptotes. And up above or earlier on, that's the true definition of horizontal. Those are the 2 big takeaways. How are horizontal asymptotes created? How are vertical asymptotes created? Because of these limits, right? For horizontal, x approaches positive negative infinity, and the limit is a finite value. Vice versa for vertical, x approaching finite value, but the limit itself is positive negative infinity. So let's do example 13. Then I think we're all done for today. Okay. See if I can actually zoom this out a tad. Okay. That's really tiny, but it's okay. So yeah, let me actually rewrite it like this. We're approaching 3 from the left. Actually, let's do the graph too. What the heck? Let's do the graph. There's an x-intercept at 2, I think, right? And y-intercept at 2/9, I think. And if I plug in -4, for example, yeah, it should be like this, I think. Yeah, that's how the graph looks. Okay. So if you're approaching -3 from the left side, of course it's negative infinity. I don't think you can really do this analytically. I don't know why it says analytically. Let's change that to graphically. You could do it numerically. What was that? Actually, you are, but that's really numerical though, in a way. So I don't know. It's kind of interesting. Yes, you can do a sign chart, sure. If you're approaching -3 from the right, that's positive infinity. If you're approaching 3 from the left, that's negative infinity. 3 from the right, positive infinity. So because of these reasons, we definitely have vertical asymptotes. One at x equals -3, and one at x equals 3. And factor form, obviously I just did that for you guys up here. So there we go. Okay. Good. We still have some time to spare at the end. So that's that. That concludes the notes for infinite limits. Squeeze theorem again, we'll talk about. It's something that does kind of show up in the it's a very, very small part. We should have that discussion. I'll do that when we come back from break. Hold on a sec. Homework. Let me figure this out. Shoot, hold on. We still can't do this one because we still haven't had enough of a discussion on extended. Yeah, we haven't done this stuff. So darn. We haven't done IVT, so we can't do that either. We could do these problems here. That's for sure. So definitely after number 3 on section B of the handout C, I know it's a little confusing. Handout C, after number 3 of section B, we do those problems, those images you see. And there's a second part to we do this also. Yeah. And did that call that sections? Did I call it section C? How I call it section C. Let me think. Can I just check? Yeah, exactly. So all section C for sure. I know it's a lot, sorry. But we need to do this. So yeah. Okay, cool.
So section C or section B?
Section C and the second half of section B.
So this one?
Yeah, the one that you see images, yeah.
After 3.
Yeah, exactly. Right. I'll put this up in Schoology right now. We're all done.